Um, I want to start thanking the organizers for giving me the opportunity to present my work and the work of my collaborators in the other side of the world. And I also want to acknowledge my collaborators, Chambon Park at the Korea Institute for Advanced Studies and Professor Cheng Li at Shanghai Observatory. I will be talking about barred galaxies and the dependence of the likelihood of having bars in galaxies as a function of environment. This is the outline of my talk. I will give a very brief introduction about the bar fraction as a function of internal galaxy properties and environment. Then I will present the galaxy catalog we construct using the Sloan Digital Sky Survey. And I will focus on two results, the bar fraction as a function of environment on different scales, and the bar fraction as a function of stellar to halo mass ratio. So we know that in the local environment, between 30 and up to 50% of galaxies have bars. This depending on the inclusion or not of weak bars. This is the bar fraction of our own galaxy catalog as a function of the expansion of the terrestrial range. For strong bars in our catalog and weak bars, in red strong and in blue weak bars, in good agreement with previous results. We also know that the bar fraction depends strongly on internal properties of galaxies, such as stellar mass or color. Focusing on our own galaxy sample, we know that strong bars in red with red lines. Strong bars are hosted in luminous, massive galaxies, typically with red colors and high concentration indexes, while weak bars are mostly found in less massive galaxies with blue colors and low concentration indexes. We also know that the bar fraction strongly depends on the morphological type of the galaxy. And even though the size of the bar decreases when we move from early to late type galaxies. And finally, there's a strong variation of the bar fraction with the gas fraction. Galaxies with large amounts of gas are stable against bar formation, or the bar is easily destroyed in those systems. So in general, this is in a good agreement between the results of many groups. But when we turn out to the bar fraction as a function of environment, we find a large variety of results. This is one early result by Lee and collaborators. They studied the environment of parallel galaxies, looking at the two-point cross correlation function. And as you can see, there's no difference between spirals with and without bars. But this group shows that the bar fraction, even at fixed absolute magnitude, is different for galaxies in low density environments and high density environments. This same group has a follow-up paper showing the bar fraction as a function of absolute magnitude and stellar mass for galaxies in different environments, in the field, in Virgo and Coma cluster. And for all those different environments, the bar fraction is different. And finally, people from the Galaxy Zoo, they show that using the marked two-point cross correlation function, that barred galaxies show an overclustering on the scales from 100 kiloparsecs to several megaparsecs. So what we wanted to do is to study the bar fraction as a function of environment using different statistics. And for that, we turn to our own galaxy catalog. It contains more than 33,000 galaxies. Among them, about 10,000 galaxies are disc galaxies. And for all of them, we have bars classified by visual inspection on combined color images. So we have barred early type galaxies. They are basically lenticular galaxies. We have also late type barred galaxies, and for this we segregate them in galaxies hosting strong and weak bars. A strong bar in our catalog is defined as a galaxy having a bar larger than 1/4 of the size of the galaxy. And finally, we have non-barred galaxies. These are just some of these examples. Lenticular galaxies with bars, strong bars in late-type galaxies, weak bars, and non-barred galaxies. These are some of our early results. This is using only these galaxies and focusing on strong bars. You can see here the bar fraction as contours in a two-dimensional place. This is the local environment, and this is the absolute magnitude, color, and velocity dispersion. And you can see that the bar fraction changes strongly when we fix the absolute magnitude or even the velocity dispersion. But once we fix the color, the bar fraction remains constant in a large range of environments. So in general, the bar fraction, once the color is fixed, has no dependence on the local environment measured in this way. But if we measure the environment in terms of the distance to the nearest neighbor, this is what we obtain. This is again contours showing the bar fraction. And as we approach to the nearest neighbor, we notice that as soon as we cross the virial radius of the neighbor, the bar fraction starts to decrease. This is made only with these galaxies hosting strong bars. Later on, we expanded our work using all the galaxies, also early types, and these galaxies hosting weak bars. And we used 4 different statistics to quantify the environment. We used the projected 2-point cross-correlation function using a spectroscopic sample of reference galaxies to study the environment at smaller scales and avoid the problem of fiber collisions in the sloan. We count neighbor galaxies using a deep photometric sample. We also use the overdensity of the local environment is estimated at a scale of 3 megaparsecs, and look at the membership of our galaxies to groups in a catalog group by our collaborators in Shanghai. So I will start with the dependence on the large-scale environment. This is the cumulative distribution function for barred and unbarred galaxies, for all the galaxies in our sample, for early and late types, and then segregated the late types, those having strong bars and weak bars. And we notice no statistical difference between barred and unbarred galaxies. So there is no dependence on the scales of about 3 megaparsecs. Then we turn to the 2-point cross-correlation function. It's not very clear here, but in black points is the cross-correlation function of unbarred galaxies, and in red points, those with bars. And this is the ratio. You should be able to see that there's an overclustering in early and late types in this range between 100 megaparsec and several 100 kiloparsec and several megaparsecs. But once we use control sample, the overclustering for late types vanishes away, and only remains that of early type galaxies. So we find an overclustering for early type galaxies hosting bars in this scale from 100 megaparsecs to several kiloparsecs. And something important is that most of our barred early type galaxies are found as satellite systems of larger groups. This is in good agreement with all the results that show that lenticular galaxies with bars are most often found in groups and clusters when we compare with the field. And this is a possible framework to explain what is happening, because probably these lenticular galaxies originally were these galaxies, when they enter to the cluster or group environment, they lose their gas, there's fading of their disk, but they preserve the stellar features such as the bar, so that's why they appear more numerous as satellite systems. Then we studied, for looking at the smaller scales, we look at neighbor counts as a function of the distance to our target galaxy for the different subsamples of our catalog, using different magnitude limits for the photometric reference sample. These are neighbor counts for barred and unbarred galaxies in the different colors. Let me show you the ratios. And as you can see, there's lack of neighbors at smaller scales for all the galaxies of our sample. But this is not found for early types. The signal comes only from late types, and it appears in both strong and weak bars. Although the weak bars, the effect goes a little further than in the case for strong bars. This is in good agreement with our previous results and some other results from the galaxy SUT-T. And it tells us that spiral galaxies hosting bars, if they are in interaction, most probably the bar is not strong enough to be preserved, or the interaction prevents the formation and the growth of the bar. And finally, we also wanted to study the stabilizing effect of massive dark matter halos, because several theoretical expectations show that the presence of massive halos help to stabilize the stellar disk and prevent the bar formation. This is a very old study by Ostraker and Peebles, but also more recent ones show the same effect. The presence of a massive dark matter halo helps to stabilize the disk and then should prevent the formation of bars. To study that, we use our same galaxy catalog. We have stellar masses. We obtain halo masses from the group catalog by Young and collaborators, and we can obtain the ratio between the two of them. This is the bar fraction as a function of the stellar to halo mass ratio, and you can see that the bar fraction is a very strong function of this ratio. As the halo increases in this way, the galaxies start to be stable against bar formation, but if we have massive stellar disks, they are able to host strong bars. You can see that also in the two-dimensional plane. This, oops. The contours denote the bar fraction as a function of the stellar and halo mass, and if we fix the stellar mass, we move in this line. As we decrease the mass of the halo, the bar fraction increases for the case of strong bars. We actually notice that the strongest dependence is perpendicular to this line that has a slope of 3/4. If we look at the bar fraction as a function of this ratio, we have a very strong dependence. And once this ratio is fixed, the bar fraction becomes independent of other properties such as stellar mass and color. So these are our general results. We find very weak or no dependence of the bar fraction on the large-scale environment. For early type galaxies, we find that overclustering on the scales from 100 kiloparsecs to 1 megaparsec. And most our barred galaxies are most frequently found as satellite galaxies of more massive systems. For late type barred galaxies, those have less neighbors than galaxies without bars, and this suggests that tidal forces might disturb the formation and growth of the bar. And finally, we find in agreement with theoretical expectations that a massive dark matter halo helps to stabilize the stellar disk against bar formation. That's it. Thank you very much.
Questions? Thank you very much for keeping to time so well.
Just to understand better, when you talk about halo mass, is this the galaxy halo, or did you derive the name of the galaxy? Or were you talking about large-scale environment?
No, it's the halo of the specific galaxy. So we have the stellar mass of each of the galaxies, and from the group catalog, we can assign halo masses to all the central galaxies. And if we focus only on central galaxies, this is the ratio between the stellar mass of the central galaxy and the mass of its dark matter halo.
So basically, the larger your halo mass, the more stable is the disk if you don't have bars.
Exactly, yes.
Other questions? Okay. Well, that's presumably the thank you in Korean.
Yeah, Korean. 감사합니다.
Okay, well, thank you. The next talk is James.
I think you just have to unplug it, James.
Okay. Yeah, that's good.
Okay, great. So firstly, I'd just like to thank the organisers for giving me this opportunity to present my work. I'm from the University of Portsmouth, and I'm doing my PhD, and my supervisor's Daniel Thomas. So what I'm going to be talking about is measuring galaxy environment in photometric surveys. So I first motivate this, and here's a picture of dark matter simulation, which shows the cosmic web, and fluctuations in the early universe have been driven by gravity, have been seeds of structure that we see in the large-scale structure today. These fluctuations and turned into dark matter halos, and then created the potential well for baryons to fall into these wells, and then galaxies formed and evolved. So it seems plausible that there should therefore be a sort of a measurable connection between the properties of galaxies and their environments. So first a bit of background. So we saw this plot in Daniel's talk already, and some work from SDSS and Baldry in 2006 shows that the mass function, and it shows that for different environments, it shows that the massive galaxies are preferentially found in more dense environments. And so it's important, therefore, to disentangle the effects of mass and environment. On the right, we've got some work from Daniel Thomas that shows the rejuvenation fraction as a function of environmental density, and it shows that for the most massive galaxies, environment is not too important, but potentially for the low mass objects, environment is important, shown by the blue curve. And then some more recent work by Peng in 2010 showed that you could separate out the galaxy red fraction in terms of the mass, the stellar mass, and the environment. So on the horizontal axis, as mass increases, you get a larger fraction of red galaxies, and on the vertical axis, as the environment increases, you also get more red galaxies. So the conclusion here is that environment is important again for low mass objects. So Sloan, as Daniel showed in his talk, the Sloan Digital Sky Survey has been sort of revolutionized the study of galaxy environment because of the statistics. But in the future, to make further progress and study galaxy environment as a function of redshift, we're going to need to study much larger cosmological volumes. And that's where surveys like the Dark Energy Survey and Euclid come in. So the Dark Energy Survey will survey around 5,000 square degrees. But it'll have, because it's an imaging survey, it depends on, you can't get very accurate photometric redshifts, and so the redshift accuracy is going to be around about 0.1, and this poses a real challenge for galaxy environment studies. So to investigate this challenge, I've been using a sample from SDSS, DR7, and so taking a fairly low redshift sample between the range of 0.02 and 0.05. On this plot here, I plot the absolute magnitude in the R band versus the redshift, and then by looking at the intersection point at my upper redshift boundary, I can create a volume limited sample. And this is the sample which is used to trace the density, so it's called the density defining population. And then I take two approaches to measure environment from the literature. On the one hand, I've got the nearest neighbour method, which I've illustrated on the left, where you essentially construct a cylinder by counting out to the nth closest neighbour, and that defines the radius of the cylinder. And then you use some sort of velocity cut to define the depth of your cylinder. And so by dividing the number, so say 5, by the volume of the cylinder, you get a density. On the other, so it's an adaptive method. Whereas on the other hand, there's fixed aperture methods where you just place down a cylinder on your target galaxy and look out a radius r, so maybe 1 megaparsec, and again use a velocity cut to define an aperture volume. So to look at the impact of photometric redshifts, what I did first was to plot the spectroscopic environment versus the photometric environment, just using the photometric redshifts available to you in the SDSS data set. And so on the left-hand side, with the nearest neighbour approach, you see the distribution is relatively smooth. The correlation between the two sets of environments falls off to 0.52, whereas on the right-hand side, the fixed aperture approach shows, particularly at low environments, that you get these sort of discrete effects where you only find 1 or 2 galaxies within your aperture volume, and so there's essentially forbidden regions on the plot. So this is another way of showing the previous plot, and I'm showing the distribution. What I find is that the distribution of galaxy environment for both the fixed aperture and nearest neighbour approaches, it becomes squeezed in the photometric case. So you're looking at a smaller range of a smaller dynamic range of environments when you use photometric redshifts. And this is because if you think about the picture of the cosmic web, by applying a redshift area, you're moving galaxies off the cosmic web. And so you're getting a smaller range of environment. Next thing I tried to look at was this relationship that Peng showed. The stellar mass versus environment so in the top I show it for the spectroscopic case, and then on the bottom I show it for the photometric redshift sample. And you can see that again this distribution becomes squeezed with the photometric redshifts, but you're still able to a degree reproduce that result even with photometric redshifts, which with an accuracy in this case of around 0.002. The next thing I looked at was because we're now using photometric redshifts with an error, it may not be that a small velocity cut is the right thing to do. So I've kind of used the brute force method and sort of iterated through a large number of large parameter space of aperture parameters. So on the vertical axis we've got n for the nearest neighbour parameter, and on the horizontal axis we've got the velocity cut that I use. So here it goes from the nearest neighbour up to the 15th nearest neighbour, and on the horizontal axis I'm going from 1,000 kilometers per second to 20,000 kilometers per second. And what I'm doing here is measuring the Spearman rank correlation coefficient between the benchmark spectroscopic environments, which I've decided to use the 5th nearest neighbour, and then simulated photometric redshifts catalogues, which I've created by displacing the spectroscopic positions by an amount drawn at random from a Gaussian distribution with a particular redshift uncertainty. And so in this plot, the largest Spearman rank correlation here is where you're comparing light with the same environment methods, which comes out at 1. But using this method, I can then explore this whole parameter space and see what happens as I crank up the redshift uncertainty. So here's a panel of 6 plots doing the same as what I was doing in the previous plot. So I've got the spectroscopic redshift sample on the top left, and then increasing the redshift uncertainty. And you can see that there's, at low redshift accuracies, or low redshift uncertainties, then there's this kind of sweet spot where the choice of velocity cut and n can really help you improve your correlation. And this slowly decays away as you go to higher redshift uncertainty. So when you get to the value of 0.1, which is the science requirement for DES, then your correlation with the spectroscopic benchmark environments has fallen off quite a lot. So these plots just show what the best parameters are from those coloured grids. So I'll just search for the best parameters that give you the strongest correlation. What I find is that the transverse parameters, so the radius and the nth neighbour, it's fairly insensitive to those values, and as a function of redshift accuracy. However, the velocity cut that you use is important as you might expect, So as the redshift uncertainty increases, then you need a larger velocity cut, as shown by the bottom two plots. So in this one, I just showed the best correlation that I got in the previous coloured grids, and showed that the spearmint rank correlation falls off to about 0.4 at a redshift accuracy of 0.1, which is the DES accuracy. So although it's dropped off, it hasn't dropped off completely, which is a good thing for photometric surveys of the future. However, in this plot, it shows that this correlation falls off very quickly at low redshift uncertainties, and then it falls off. It kind of plateaus off as you go to larger redshift uncertainties. So to really get the benefit, you need to get very, very strong redshift uncertainties. So just summarise. So the photometric environment distributions have a smaller range, a small dynamic range than spectroscopic environment distributions. This is because the redshift areas tend to smooth dense regions into the surrounding less dense regions. The red fraction dependence on mass and environment is possible to reproduce this result even with photometric redshift data. And correlations with the spectroscopic benchmark varies with the aperture parameters and particularly the velocity cut. Environment signal is still present in simulated photometric redshift samples, even with large redshift uncertainties. This is mostly due to the angular distribution of the galaxies. And that's all, thanks.
You kept the time very well too, thanks. Questions? Simon.
This is more a comment in a way, which is I think there's an additional in-between layer we can add in to improve the photometric accuracy of this, a lot. And that's if we have a deeper imaging survey that takes place on top of a spectroscopic survey, we can fold in spectroscopic priors. In particular, if we know and have found a group catalogue, then if you find a photometric redshift that's in the vicinity of that group catalogue, it's likely to be associated with that group. And that means we can very, very quickly, if we have a combined spectroscopic and photometric catalogue, improve the photometric analysis such that you might not need a 4 to 13 times larger sample. So if we combine the two together, I think we can do something even more powerful than do one or the other.
Yes, I've seen some work by Kovac, I think, Katerina Kovac, who applies sort of technique to modify the redshift distribution based on spectroscopic values and whether you're close to a group, or, as you say, and that will push you closer towards give you a higher correlation on your environment.
Other questions? Over there in the Matt.
So I'm just wondering why you don't incorporate the full probability distribution of the photometric redshift, because that informs on how accurate your aperture should be, or how broad your aperture should be, for instance. So are you plans to do that, or?
So I have looked at that in brief, but I guess I fell into a fairly large parameter space already because I had the nearest neighbours and the velocity cuts for the range of redshift uncertainties to then fold in the photometric redshift probability distribution. So you might have to use some sort of Monte Carlo approach to withdraw positions from that redshift distribution it added an extra layer of complexity to this analysis. So I kind of started simpler, but I mean that could be built in at a later time.
Maybe you showed it and I didn't see it, but have you tried changing the fixed aperture size?
Yes, so there's another set of plots like this which I don't show that use it, but instead of having the nth nearest neighbour on the vertical axis, it's got the radius of the fixed aperture. So I get another set of plots like this. And then the optimal values for the velocity cut and radius are then on the the two right-hand plots on this figure.
And you don't find any correlation in like you better reproduce the environment using a fixed aperture better than another? Or?
No, there's not a lot of difference between the two. I find that the nearest neighbour approach works very slightly better, but not a lot.
Anyone else? Okay, thank you very much. And the final talk this afternoon is Jonathan Elliott from Max Planck Casting. Apart from Massimo's talk this evening, that is.
All right. So for those that are still awake and don't know me, I'm Johnny Elliott. I work at the Max Planck Institute in Garching. I'm also British too. They seemingly put us all in the same slot tonight. Despite my German accent, I'm not German. So I'd like to talk about some work that was carried out with this collaboration called COIN, which stands for Cosmos Statistics Initiative. The idea is that we want to bring statistical ideas over to astronomy that are not usually used for situations where they could be, and much more simple than techniques that are normally incorporated. Because we wanted to help you so much, we spent our entire summer locked away in an apartment writing software. Okay, so let's get on with it. So the point is, a lot of people want redshifts. They can use them for studies in cosmology, looking at supernova rates, stuff like this. So let's just take for granted people want redshifts, and it's a property we want. So most of the time you want to do it spectroscopically because you can look at the emission line, the absorption line, you can then find the redshift. Unfortunately, this is a bit expensive, and especially as the larger your samples get, the more expensive it gets, obviously. Especially as we've already seen today, lots of talks with, okay, you can insert your favorite sky survey here, I'm a bit biased. And we'll be having lots of more data coming, and over 20 billion sources, at least for the LSST. And so this is basically impossible to do spectroscopically. But as we also know, it's less time consuming to just go away and do the photometric redshifts. So when I say photometric redshift, for those that don't know already, the spectrum of your source is characterized by a lot of things. So for example, for galaxies, they're characterized by the masses, the ages, the metal content, dust, etc., but also the redshift. So you can use the photometry to pull out this redshift. For this, there are usually two common techniques used. One usually referred to as template fitting techniques, and the other one is empirical machine learning techniques. So the template techniques, we've seen a few already today, is you basically synthesize a bunch of spectra for your source. So for example, for galaxies, you use stellar population models, and then you go away and you fit these to your photometry. These are, of course, then going to be heavily dependent on the spectral templates that you use. So, for example, there's Hyper-Z, LaFar, Zebra, there's a whole bunch of different template fitting techniques. The second avenue to try is this empirical route. And the idea is you take a sample of known measured spectroscopic redshifts, where you also have the photometry, and you pick some way you want to fit one to the other. So, for example, here I have a neural network. And then you use this fit to then predict for the one that you have the photometry redshifts, but not the spectroscopic redshifts. And then, of course, these are then heavily dependent on the training set and the technique you use to train them and the function used to fit them. So, for example, there's neural networks, decision trees, polynomial fitting, etc., etc. Okay. So statistics is actually something very nice to use instead of these more complicated techniques, and it's very close to, or is essentially the same as linear regression. From a set of models called generalized linear models, or GLMs for short, and they're actually very appropriate for photo redshifts, for photo Z calculations, which should become apparent in the next few slides. The most important things, or the most interesting things to take for GLMs is you can firstly pick a distribution that reflects the realistic range of the property you want to predict. The second thing is if you have a system where your variance depends actually on your mean or expectation value, you can't use simple linear regression. It handles where, for example, in a lot of places you take your data and you see it's a power law or it's log normal, and then you log your y-axis and you use normal linear regression. But this is does not always represent exactly your data and how you should actually tackle this problem. If, for example, here this is not the same. And they're well studied. So there's a bunch of software that's freely available to use. People know how to use it. It's well documented, but it's just written in such a way that it's not nice to approach for an astronomer. I'm going to show a lot of formulas, but you can ignore them and just take for granted the words that I say, because maths can get a bit tiring. So the first idea is that you can take any exponential family. So when I say exponential family, this is just binomial, normal, Poisson, gamma. You can look on Wikipedia for exponential families, but there's normal probability distributions. They should all be rearrangeable into this form here. And then from this, you can then quickly determine your expectation value or your mean, and you can also handle your variance. So your whole system, you want to basically just parameterize with one parameter. You can now forget this slide. And the second important thing is, as I said before, if your data is not linear so if your measured values are not linearly connected to your y values, then you need to link them somehow. And so this is what this parameter here will do. So I quickly try to make it make more sense. If you take a normal Gaussian for your linear regression, so here's the Gaussian, you can rearrange this formula here, and then you pull out what we all know, that the expectation value was just your matrices multiplication of your measured x with some parameter set beta. And then your variance is just the sigma squared. So you can now describe your entire system with this parametric value here, beta. Okay, but for the photometric redshifts, it's a bit more, well, not difficult, but we have a different set of criteria that we want to have positive and continuous numbers, because a redshift of -1 doesn't really make sense for our predictions. I guess that would be a Nobel Prize if I measured one. And so we want to use the gamma family, which this works for. So the gamma family is positive and continuous. You go and find the formula, and it's this one. And now this is the generalized linear model representation here. And then you can easily pull out, again, the same criteria that allows us to then see that we can describe the entire system with this parameter data on the right-hand side. And so you see it also handles the case that your x values are not linear dependent on the y values, but contains it within the entire formalism. And also that your average is also linked to your variance, and so it also handles this. So to actually test this and see how good it is at actually predicting photometric redshifts, we looked at two different samples of galaxies. The first one is FAT0, which are synthetically created redshifts using template techniques. There's around 200,000 galaxies with 11 different filters. And then a realistic data set from the DR10 of the Slow Digital Sky Survey, and this has around 1.5 million galaxies with 5 different filters. We carry out a simple methodology, very similar to a lot of machine learning techniques as I described at the beginning. So you randomly want to split your sample into training and test sets, or in the case where you want to actually apply it, you have the one where you have your measured photometric redshifts and spectroscopic, your measured photometry and spectroscopic redshifts, and then the sample where you don't actually have any spectroscopic redshifts. This step I won't go into a lot of detail, but you can carry out some component analysis and actually find that you don't need to use all your filters. So for example, if you have 11 filters, you can get similarly robust answers by looking at only 6 filters. And this is primarily here to make things faster, if you want the option to make things faster. And then simply you take your training set and you fit the generalized linear model, getting this beta parameter to represent your data. So not so complicated. And so I quickly show you here that on the y-axis you have the photometric redshifts, on the bottom you have the spectroscopic redshifts, on the left-hand side is the FAT0, and on the right-hand side is the SDSS. The key point to take away from this is that we achieve competitive and or complementary values to those in the literature for other techniques involving template fitting and other machine learning techniques, and they're of the order of 1%. I'm not really here to try to advocate too much that you should replace the techniques that you use, but that this is a complementary idea. The bonus that this technique has is, A, it's predicting values that make sense. So you don't have any negative values, they're all positive and continuous. The second bonus, as I've already pointed out, is that, so for example, on the right-hand side panel here, you can consider the catastrophic error as how well your fitting is doing. And so you also see that the number of components of what we say the number of filters, you can get down quite easily to 6 filters, and you still get a similar robust technique. And this is important in terms of how fast you actually want to do something. So this only takes hundreds of seconds to complete, as opposed to the thousands of seconds. And then this is also tied to the size of your samples. So the bigger the samples you want to look at and train with, the longer it will take. So this is the bonus of GLMs is that they're much faster than a lot of techniques that require large sample sizes and need to use all the filters. But the aim of COIN was actually to make statistical tools to actually, let's not say the word that astronomers are not necessarily lazy, but they don't like necessarily to new ideas where it takes time to learn and how to use them. So what we did was we made a bunch of tools in commonly used languages. So R, well, I wouldn't say R is commonly used in astronomy, but it's very much extensively used in statistics. And then also a Python package used quite a lot now, I think, in astronomy. And also an online web tool where you can basically don't have to think or do much other than click buttons, which I think a lot of people prefer. So I quickly do actually a demonstration of our web tool. Okay. So the first hardest thing is you have to type in the link at the top of the web page, and it loads this web page here. Now most of this is just text. It looks like it's going to be really difficult, but no, this is just describing everything I said to you and other little details if you need them. The most important things to see are on the left-hand side. So you have a browse button here, so you will select your data set for training. So you have your photometric measurements, you have your spectroscopic redshift. You enter here, then down here you now have the galaxy sample where you don't have your spectroscopic redshifts, and you put it in here. And then you just go down to the bottom and you press Run Analysis. I sound like a robot now as well. Anyway. Once you do that, then there's a whole selection of different diagnostics on the top. So for example, you have the area distribution, which just plots the spread of your delta z's over redshift as a probability densities. You also have the same thing, but in redshift boxes across redshift and bins. So you can actually see how well the GLM is doing over redshift, and if it's properties of the technique, or if it's related to your training set. And then, as I showed you before, the same plot as your photometric redshift against your spectroscopic redshift for your training sample, and how well this is doing. And then there's also a selection of diagnostics if you want to use them. So this tool is freely available. You can use it for your samples. You can put them in and try it out. Okay, so hopefully I've not gone over my time yet. So the Cosmos Statistics Initiative is a group of people that want to build a bunch of software for you to use for free. If you're interested to find out more about the organization, you can go to this webpage here. We created a bunch of web tools and freely available software. So also, I didn't go through the R packages and the Python packages, but you can use them within 5 lines of commands on your terminal, and you should be able to go away and fit your photometry redshifts in a different method than conventionally used. Thanks for listening.
Right, you won't have had time to download it and try and use it yet, so the real questions probably come later.
So this method can substitute template, but the template will have always the advantage that you can derive physical properties of galaxies. So from what you have shown, I couldn't get an advantage of this method in that you recover catastrophic values, failure, of those typical surveys. So the method didn't do better. So what is the advantage? For example, have you thought of how to distinguish that common problem in photo Z happens at very high redshift when you have a few photometric data points and you want to distinguish redshift 6 sources close to real ionization from redshift 2 galaxies? And actually, we would like to talk to you afterwards because we are having such a problem with pixel data. And I doubt that the blind statistical approach would be able to solve it. Have you thought about that?
Yeah, okay, so my first comment would be, I don't think it's necessarily to replace the template fitting techniques. Actually, a lot more, it's becoming quite normal to actually look at hybrid techniques now, so combinations of different ones. Of course, you can't, like you said, you can't take out the physical properties of anything else apart from the photometric redshifts. But the main advantage with this one is that you are fast and you don't need big training samples. So it's not necessarily to be used always for galaxies, but for example, for transient surveys, if you want to decide straight away to do spectroscopy, this is a much faster and cleaner technique than if you want to train on samples that can take hours.
So when you train much faster, how faster?
Okay, if you want to do it on the FAT 0 with 10% of the samples, so 30,000 with all 11 filters, it takes, I think I put 1,000 seconds. If you reduce the filters to 6, it takes 100 seconds. And the difference between the how well it fits is not so large. So actually the main point comes from this component analysis, but not the actual sample sizes. So you can train it on relatively small samples that are well represented of the entire system, and it still is as good as it would be if you did the neural network technique, which requires a much larger sample sizes to learn on. And I forgot the end question, the high redshift.
Oh yeah, trying to distinguish. There the neural network cannot be applied anyway because you lack the training set.
Yes.
So redshift 6 versus redshift 3.5.
No, we
interesting to check.
Yeah, that'd be interesting.
Yeah.
Other questions? I thought I saw another one. Okay, I guess you all want to arrest. Nicola, are there any announcements for tomorrow? Well, hold on, before. all the speakers for giving me an easy job because you won't get the time. Thank you.
For the shuttle bus, you will depart at 6:30 in front of the Bosco Monte, and there is a room for other people that wants to have a walk in the city center because we are queued for the bus.